Hello everyone. Today we are going to analyze this frame using strain energy method. In this frame there is a beam AB and a column BC. In the beam there is no load. In the column BC we have a point load 48 kN. It acts in the center. Length of AB is 4 meter and the height of BC is 6 meter. Now let us find the degree of static indeterminacy. In the point A, there is a fixed support. In the fixed support, there will be horizontal reaction, vertical reaction, and movement. In the point C, there is a hinged support. In the hinged support, there will be horizontal reaction and vertical reaction. So the number of unknown reactions and moments are 5. The available equilibrium equations are 3. The degree of static indeterminacy will be 5 minus 3, so it will be 2. Let us keep the horizontal reaction at C, HC, and the vertical reaction at C, VC, as redundant. Let us keep this point as D. We know the formula for the strain energy due to bending. In this frame, we have to make sections. There are three different parts, AB, BD, and DC. So we have to make three sections, one in AB, one in BD, and one in DC. You can see that I have made three sections. These two sections at a distance of x from C, and this section at a distance of x from B. Since there are three sections, we have to split the formula into three parts. This is for this section. Here the limit is 0 to 3. This is for this section. Here the limit is 3 to 6. And this is for this section. Here the limit is 0 to 4. We are going to find the moments M1, M2 and M3. We need to follow left hand side rule. Clockwise will be negative and anti-clockwise will be positive. Let us find the moment M1. Up to this section we have HC and VC. For VC there is no perpendicular distance, so we should not consider this. HC is acting in the anti-clockwise direction, so that it will be positive and the distance is x. So HC into x. HC and VC are the redundants. So by them we have to partially differentiate all of the movements. First let us partially differentiate M1 with respect to HC. For HC it will be 1. 1 into x it will be x. Let us partially differentiate M1 with respect to VC. Here there is no VC, so the differentiation will be 0. Now let us find M2. Up to this section we have HC, VC and the load 48. For VC there is no perpendicular distance, so we should not consider this. HC is acting in the anti-clockwise direction, so that it will be positive and the distance is x. So HC into x. This load is acting in the clockwise direction, so that it will be negative. For this load we have to take this distance. This distance is x minus 3. Then we can multiply minus 48 with the x minus 3, so that we will get this. Let us partially differentiate M2 with respect to HC. For HC it will be 1. In these two terms there is no HC, so the differentiation will be 0. 1 into x it will be x. Let us partially differentiate M2 with respect to VC. In these three terms there is no VC, so the differentiation will be 0. Now let us find M3. Up to this section we have HC, VC and 48. HC is acting in the anti-clockwise direction, so that it will be positive and the distance is 6. So HC into 6. 48 is acting in the clockwise direction, so that it will be negative and the distance is 3. VC is acting in the anti-clockwise direction, so that it will be positive, and the distance is x. Minus 48 into 3, it will be minus 144. Let us partially differentiate m3 with respect to hc. For hc, it will be 1. In these two terms, there is no hc, so the differentiation will be 0. 1 into 6, it will be 6. Let us partially differentiate m3 with respect to vc. In these two terms, there is no vc, so the differentiation will be 0. For vc, it will be 1. 1 into x, it will be x. In the point C, we have horizontal reaction Hc, so the horizontal deflection will be 0. When we partially differentiate the strain energy U with respect to Hc, we will get the horizontal deflection in the point C, which is 0. Let us partially differentiate U with respect to Hc. When we partially differentiate m1 square with respect to Hc, we will get this. When we partially differentiate m2 square with respect to Hc, we will get this. And when we partially differentiate m3 square with respect to Hc, we will get this. We can eliminate 2. 1 upon Ei is common. We can take it outside, and on the other side, 0 into Ei, it will be 0. Now let us apply the expressions for m1, m2 and m3. Also, let us apply the partial differentiations. X into x, it will be x square. We can multiply this term with the x so that we will get this. And we can multiply this term with the 6 so that we will get this. After integrating and simplifying, we will get this equation. Let us keep this equation as number 1. In the point C, there is a vertical reaction VC. So in the point C, the vertical deflection will be 0. When we partially differentiate U with respect to VC, we will get the deflection in the point C, which is 0. When we partially differentiate these three with respect to VC, we will get these. We can eliminate 2. We can take 1 upon Ei on the other side. 0 into Ei, it will be 0. Then we can apply the expressions for m1, m2 and m3. Also, we can apply the expressions for the partial differentiations. When we multiply this term with a 0, it will be 0. And when we multiply this term with a 0, it will be 0. When we multiply this with the x, we will get this. Then after integrating and simplifying, we will get this. Let us keep this equation as number 2. We can take a calculator and solve these two equations so that we will get Hc and Vc. We know that in this frame, there is no vertical load. In this case, the values of Vc and Va will be same, but they will be acting in the opposite directions. Vc is acting upwards, so Va should be acting downwards. Then using this rule, we can find Ha. To find Ma, let us take moment about A from C. Vc is acting in the anticlockwise direction, so that it will be positive, and the distance is 4. Hc is acting in the anticlockwise direction, so it is also positive, and the distance is 6. This load is acting in the clockwise direction, so that it will be negative, and the distance is 3. Let us assume that Ma is a hogging moment, so it will be acting in the anticlockwise direction, so it is positive. For Ma, we will get minus 18. That means our assumed direction is incorrect. Ma is not a hogging movement, it is a sagging movement. We have to change the direction. You can see that I have changed the direction into clockwise. Using the right hand side rule, we can find the shear force values for the beam AB. For the beam AB, there are only two perpendicular forces, this one and this one. Using them, we can find the shear force values. Now let us take the column BC. Here there are three perpendicular forces 30, 48 and 18. Using them we can find the shear force values. Suppose it is difficult, you can assume that BC is horizontal. In the point B we have 30. In the point D we have 48. And in the point C we have 18. Now using the right hand side rule we can find these values. Here you can see the shear force diagram. Using the right hand side rule we can find the moments in the point A and the point B. Let us find the moment at A. In the point A we have MA which is acting in the clockwise direction so that it will be positive. Let us find the moment at B. MA is acting in the clockwise direction so that it will be positive. BA is acting in the anti-clockwise direction so that it will be negative and the distance is 4. Finally, we will get minus 36. We know that the point C is a simply supported end, so the moment will be 0. To find the moment at D, we can use left hand side rule. For VC, there is no perpendicular distance, so we should not consider this. HC is acting in the anti-clockwise direction, so that it will be positive and the distance is 3. For the moment at D, we will get 54. Here you can see the bending moment diagram. If you plot this diagram in the opposite sides, that is called the bending moment diagram on the tension side. Alternatively, we can draw the bending moment diagram by superposition method. First, we need to draw the free moment diagram. Then we have to draw the end moment diagram. When we combine both of them, we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.